Okay, let's do more of this homework. I did 1 and 2 and 4. I jumped ahead to do 4 because it didn't have any trig functions in it, so I just felt like it. I think all the rest have trig functions, so we'll bust them out. Ooh, 9 doesn't, but that's fine. We'll come back to it. What's 9 trying to do? I'm not sure. All right, we're going to do 3. So for number 3, you're seeing tan and you're seeing secant, so you should be thinking hyperbola. But in this case, you should not be thinking hyperbola because secant is squared and tan isn't. So if I want to use that Pythagorean identity that says that secant squared t minus tan squared t equals 1, then I only need to square the x equation. So I would go x squared equals tan squared t. I'd leave this one alone, so it's still y to the 1 equals secant squared t. Now I'll subtract these equations, but I'll subtract them in the order of y minus x equals secant squared minus tan squared. I screwed that up, of course, it's x squared. Secant squared t minus tan squared t. And that's a trig identity that just becomes 1. So by subtracting these things, my parameter is eliminated, and I have a y that equals x squared. Brr. I have a y minus x squared, and it equals 1. Geez, I'm not doing so hot. So what do? I would add this to both sides. I would get y equals x squared plus 1. And we don't really want a plus 1 here. You probably haven't had time to really memorize this, but the conic section, well, I mean, whatever. You could leave it like this, of course. But if you were trying to do the conic sections thing, then it would be y minus k equals 4p x minus h squared. So just notice that in this form, there's nothing being added on to the guy that's getting squared. So this plus 1, you'd want to subtract it and go y minus 1 equals x squared. This would be the conic sections form, and that would be acceptable. This is sort of the standard form. That's acceptable too. Of course it is, because that's much easier to understand. You guys know that one better. So the problem now is we've got, well, a big problem, which is that I'm sure pretty much all of you would love to just graph this rectangular equation and say that, well, it's obviously x squared plus 1, so obviously it'll have its vertex at 0, 1, and the coefficient is 1. So I know I can go left 1 up 1, left 1 up 1, I can go left 2 up 4. Get the other one over here, and I'm just going to get this nice, beautiful, simple parabola that I've been studying since Algebra 1. And I want to say you're right, and maybe you even are. But are there any restrictions placed on t? Actually, no. T can be anything it wants. We're assuming that t can be anything from negative infinity to infinity, but that's not the only way to restrict a function's domain. Just using tangent? Well, no, that won't be a problem, because of course if I were to graph tangent, it goes zoop. And we see that tangent will give me all the outputs from negative infinity up to infinity. So the fact that this graph seems to have a domain of all reals, I don't have a problem with that. The outputs of tangent are in fact all real, so that seems fine. I am a little nervous about this other guy though, where it says y equals secant squared. So what's secant squared? Well, to understand secant squared, you better understand secant first of all. Secant at 1, secant is cosine. Yeah, so we get this guy that goes bloop, and then we get asymptotes. Then we get this other guy down here at -1 that goes bloop. Then we get this other guy that goes bloop. But remember, this isn't secant, this is secant squared. So all these positive guys, if you square them, they'll just get a little bit bigger and stay positive. But all these negative guys, they'll turn positive. They'll kind of reflect up and go bollop. And then this positive guy will go bollop. And then this negative guy over here will go bollop. So we are getting in secant squared a function whose outputs are from positive 1 to infinity. And guess what? Our parabola only goes from positive 1 to infinity. So by parameterizing this parabola in terms of tan and secant, I actually have not affected my domain or range at all. I do still get the same things that I would have expected to get, which is a domain of all reals and a range that goes from 1 to infinity. I don't know if there's a heck of a lot more to say about this. We should probably do the starting point in the direction of growth thing. Based on the fact that tangent equals 0 at 0, I can see that when t is 0, my x will be 0. So that starting point is definitely where t equals 0. And based on the fact that I see that as t increases, my x's are going to increase, I can see that my direction of growth is this way. But again, this half of the parabola would only be generated by the positive t's. So what happens when t is negative? Well, the negative t's would generate this half, and they would do it by coming back in from the other side. It's kind of weird. Let me show you. I'm going to try to do this, see if this works. I'll turn this window on. Okay, so here's Desmos. I've parameterized the thing. It's the parabola that we thought it would be. I'm going to move it over just because. And I'm in, radian mode. So see how this point, I can control that point by just using the slider? Well, I'm only going from negative pi to pi. If you think about it, the domain of tangent, not the domain of tangent, but the period of tangent was only pi. So I'm going to get every single possible value of x just by going from 0 to pi. I could actually start at 0 if I wanted to, but I needed some negative ones. But if I went from 0 to pi, I'd still see the whole thing. But look what happens when I start at 0. We start at the vertex, and as we grow out, 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 out. But by the time I get to pi over 2, tangent is already heading off to infinity at an asymptote. And then when you cross over, you start rushing back in from the other side. It's, oh, here I am. Look, here I am, coming in from the other side. So it's really kind of weird. But if you start at 0, then you start in the middle, and then 0 to pi over 2 generates the right-hand side, and then pi over 2 to pi actually generates the left-hand side. So it's like, I don't know, you go this way, then you fall off the face of the earth, and you just come back in from the other side of the earth. I don't know. Maybe that feels weird. Probably does. I do not know how to make that look good, but if we could like color code this or something. I've seen that done before. They do that in math actually kind of a lot. But like think of the colors of the rainbow. So my first bits of change here are in red. Then the rainbow would start going, oh, we keep going, red, orange. Then in yellow, we'd see some yellow. Then green, red, orange, yellow, green. Well, the green says we're coming in from here now, green. Then the blue says, okay, we're still increasing until we finally get to indigo. Here comes the indigo, and finally the violet. So, you know, oh, you didn't even see what I just did. Oh, it's so good. You guys missed it. Okay, let me take this thing away. Hey, look. God, I'm not going to ask you to do this, but hey, what if you had a red, orange, yellow, green, blue, indigo, and violet magic marker? Could you really mark the hell out of your graph to indicate how this thing changes? Well, yes, you could. You could start from 0, and as we grew from 0, you would kind of see that this is how this thing actually changes. You start from the middle, and you go out to the right, and then somehow, kind of weirdly, you teleport back to the left, and then you continue to come back in. So I don't know. Hopefully that's sort of a helpful thing to have seen. I like it. I'm glad I did it. Let's go on. We did 4. Let's do 5. I don't want to do 5. You guys are good at ellipses, aren't you? Isn't 5 an ellipse centered at the origin, and the major axis has a length of 6 and it's vertical, and the minor axis has a length of 4 and it's horizontal, and that's fine. Let's not do it. Okay, fine. I'll do it. But seriously, I talked about this already. I think probably you're fine. I don't see anything getting added on, so I must be adding a 0 and adding a 0. Those numbers are my center, so I'm centered at the origin. Then the coefficient of the x equation here is 2, so I guess I'm going left and right by 2. Those are going to be my co-vertices, because that's my shorter axis. Then this coefficient is 3, so I go up and down by 3. Those are going to be my vertices, because those are the ends of my major axis. And that's literally it. I'm just going to zoom way the hell in on this. And I'm going to use my ellipse drawn tool. View. So there it is, the world's most perfect ellipse. Throw that in the garbage, throw this in the garbage. Just keep this guy. Alright, so the only thing left to talk about then is how do you actually show algebraically how to convert this into rectangular form? I'd like to think that you don't really need algebra to convert this to rectangular form, because you know that the rectangular form should be x minus h all squared over a squared plus y minus k all squared over b squared equals 1. So that would mean this guy with its center at the origin, this would be 0 and 0, giving me just an x squared over and a y squared over. Then a is the distance from the center to a point at the end of the horizontal axis. It's this distance here, which is 2. So the 2 squared is 4. And then the b value is the distance from the center up to the end of the vertical axis. So it's this distance here, which is 3. So chuck a 9 down there, and it equals 1. There, I did it. I've technically converted to rectangular form. I didn't do any math to do it, but I did it. But like I said, that's not going to cut it. You do have to show the algebra. So the algebra that you would show is squaring both sides and then solving. Now if you square both sides right away, you would get x squared equals 4 cosine squared t, and you would get y squared equals 9 sine squared t. Then you go to add these things together, you get x squared plus y squared equals 4 cosine squared t plus 9 sine squared t. And then all hell breaks loose, because you can't factor anything out. If you try to factor out 4, then sure, the 4 goes away, but you'd still have a coefficient of 9/4 on this, and you couldn't use the Pythagorean identity. If you try to factor out 9, then you still have a coefficient on cosine. If you try to factor out the least common multiple, like a 36, that might sound good. Factor out a 36. Then you have cosine squared over 9. You have sine squared over 4. And just, it's not working. So this is why I told you that you got to isolate those trig functions first. So you divide by the 2 first. Then you square. Because you need to have just plain old cosine squared. So you get y minus 3 equals sine of t. Now I'm free to square both sides, getting an x squared over a 4. That equals cosine squared, and getting a y squared over 9. That equals sine squared. Then I can add these two equations together, getting an x squared plus x squared over 4 plus y squared over 9. That equals cosine squared plus sine squared, so it equals 1. There you go. So this is the algebra I'd need to see. I would want to see you dividing both sides by 2, then squaring both sides, then adding them together. But that's it. What else do I expect from you? I do expect you still to be indicating where t equals 0, and then the direction of growth from there. So if x is defined by a cosine function, well, cosine functions start at their max. So that's telling me that when t is 0, this x equation is going to start at its max, and its max is 2. this y equation starts on its midline, which is 0. So kind of unfortunately, a lot of these seem to be starting right at this point here. If this were a clock, they all seem to be starting at 3 o'clock. But we could definitely start at 12 or 6 or 9. And of course we could start anywhere else in the middle, but you know, that would be a little weirder. We're typically going to start north, south, east, or west. And all of these keep starting west, but we won't always do that. The easiest way to start somewhere else is just to make this one sine and make this one cosine, because if I did that, nothing else would change here except for my starting point. Suddenly x would be the equation that starts on its midline, and y would be the equation that starts at its max, and suddenly my starting point would not be over here east. It would be the north one. You'd start up top instead. Hopefully you get that. Anybody want to hazard a guess as to how we could start over here at 9 o'clock or 6 o'clock? The answer is make one of these things negative. If this was negative, I don't know why I made them both negative. Maybe I had to. But if the y one was negative, then obviously cosine wouldn't start at its max anymore. It would start at its min. So if there was a negative there, then suddenly, boop, you'd be starting down there. So just for funsies, let's pretend that was actually the one we had. Then you would mark that this is t equals 0. And then from there, which direction do I want to rotate? Well, the x equation is still a sine equation that's positive. So you would still want to rotate in the direction of increasing x's. So you'd rotate from here. You'd come around counterclockwise. So maybe you can tell by that discussion we just had that if I did put a negative here on the x equation, it'd still be the same graph. The only difference is we would start here still, but would rotate this way now instead. Because now you have a sine function that starts on its midline and decreases. So that direction, that initial rotation direction would be in the direction of decreasing x's, meaning left, and around we would go. And around we would go forever and ever. I hope that made sense. I say that a lot. Moving on. Number 6. Number 6 is gone. That's problematic. But not that problematic, because I can just do this. Yeah. Alright, so here's 6. What's this? What'd you say? It's an ellipse. Yeah, you're right. You guys know you can fast forward, of course. If someone needs to hear this, I'm going to do it again, but I'd like to think that most of you know how, so just fast forward. If you need to hear me talking about these secant ones and the one where tangent is squared and all that, just fast forward. But if it helps somebody to hear me talk about this again, I will. But again, why am I making light of this? Well, because I think I already told you. These numbers on the end here, this is your h and k, which gives you your center. If you do enough of these problems, then you know this, just by looking at it. So this would be a transformation up 2. That tells me my center will be at 2. This would drag me down. Yeah, okay. This one would drag me down, so my y would be at -1. So 2, -1 is right here. And then again, the coefficients just tell me how far to go. So the coefficient on the cosine function in the x equation is 2, so I'm going to go left and right by 2. I'll go here, I'll go here. And the 3 says go up and down by 3. So if I go up 3, 1, 2, 3, and down 3, 1, 2, 3. So how similar is this to the last one? 2 and 3 cosine. Yeah, okay. So hopefully what you can tell is the only difference is that we got translated. We got pushed to the right by 2 because somebody added 2 to our x's, so we got pushed to the right by 2. And somebody took 1 away from all of our y's, so we went down by 1. Other than that, it's the exact same graph as number 5. So, beep. There you go. So I'm not going to say more. Yes, I am. I'm still going to show you the algebra one more time. So the algebra, again, I talked in the last problem, number 5, about how it was important to isolate the trig functions first. And that takes 2 steps, suddenly. We would subtract this 2 first to get x minus 2. Then we would divide by 2, which puts a 2 in our denominator, and it equals the cosine of t. We would do the same with y. You'll add 1 to both sides first, then you'll divide by 3. Now from here you can square both sides. So you'll get x minus 2 all squared. And don't expand that out, just leave it alone. You'll square the 2 as well. Your denominator goes to 4. That's going to equal cosine squared. Do that again to the y equation and you get a y plus 1 that's squared over 9. And that equals sine squared. Okay, and that means if I just add these together, then I'll now have an x minus 2 all squared over 4 plus y plus 1 all squared over 9 equals 1. And you now have your rectangular equation. That's it. All right, 7. So we haven't done this yet, but this one will be a hyperbola. You sort of know that it'll be a hyperbola because this time, instead of a sine squared t plus a cosine squared t giving us 1, we need to use the other form of the Pythagorean identity that says that a secant squared t minus a tan squared t equals 1. Which means instead of getting an x squared plus a y squared to get a ellipse or a circle, we're going to get an x squared minus a y squared. I don't know if I just misspoke. An x squared plus a y squared would be an ellipse or a circle, but this time we're going to get essentially an x squared minus a y squared, right? As we do this math, that'll equal 1. There'll be denominators too. I don't mean to glaze over that, but this general form, that's going to be an ellipse for us. So we know that right away because the functions are secant squared and tan squared. While I have your attention to that issue, I should probably point out that it doesn't really have to be secant and tan. It could be the other functions that are kind of similar. If I divided through by sine squared, yeah. Imagine if I started with this red Pythagorean identity, but I divided through by sine squared, then you would get 1 plus cotangent squared equals cosecant squared. What am I doing? Are you yeah, these are supposed to be t's. Okay, so that would mean that we could also use an identity where the cosecant function squared minus, because I would subtract this from both sides, the cotangent function squared. That equals 1. So not much about this would change if instead of secant I gave you cosecant and instead of tangent I gave you cotangent. You would still go after this problem in exactly the same way. You would still get the same relationship of an x squared minus a y squared. You'd still get a hyperbola that opens left, right like this with its asymptotes. So what would change? I don't know. Honestly, maybe nothing. I think the starting point would change. Maybe instead of starting right on a vertex, then I think we would start at infinity and come running back into that vertex. But that's all. All right, again, I've said too much. That didn't work. Oh, this is so much. Okay, so let's just do it. We know it's going to be a hyperbola, so how do we get there? I would definitely add 1 to both sides. So I have x plus 1 equals secant t. Then I have y minus 2 equals tangent of t. Now you guys can't switch colors like I do, so if you had to stick to all one color, maybe you draw a little line here indicating that you're now moving on to your next step. I'm squaring, so I now have x plus 1 all squared equals secant squared. equals tan squared. All right, line, 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 draw a line. My next step would now be to subtract these things, and I have to do it in the order of the x's minus the y's. So it'll be x plus 1 all squared minus y minus 2 all squared, and it equals 1. Now don't be fooled. This kind of looks like it might be the equation of a circle because there's no denominators, right? Maybe you've kind of picked up on the fact that with a circle there's no denominators. But no, that's not true. Oh no. Give me a minute to fix this glitch. Okay, this is still a hyperbola. I did not fix this glitch. Alright, this is still a hyperbola. Technically your denominators are 1 and 1, which would mean that if we were trying to graph this, which we are trying to graph this, we'd use the h and k to plot our center, which is at -1, +2, right here. And then if these denominators are 1 and 1, then I guess it's just telling me to go left 1, right 1, up 1, down 1, and we would get a little rectangle that's just a square. But that square does just as good a job at defining our asymptotes as any rectangle could. Oh, trying not to let my eyes slip. All right. Great. Oh, I think I messed that one up. All right, so that would mean my hyperbola, let's see, x is first, so I go in the x direction. So this is my vertex here on the rectangle, and I go this way. And I'm not. Oh, it's so bad. I don't care. I'm not fixing this. Go. Oh, that's so bad. All right, I can live with it. There you go. Okay, I'm happy with it. Moving on. Number 8. It didn't do what it was supposed to. All right, so for 8. 8, hopefully you know what this is going to be. It's going to be a parabola. And again, that's because tangent is already squared, so I will not need to square x. I will need to square y though. So I'll end up with an x minus 2 that equals tan squared. I'll end up with a y plus 1 that does need to get squared so that I can get a secant squared. Then from here, now that everything's all set up, I need to subtract these, but I need to subtract them in the order where the secant squared comes first. And since I have to subtract them in that order, it means I have to subtract them where the y plus 1 squared comes first, minus x minus 2, in parentheses. All right, so that means I've got this equation where a y plus 1 is getting squared. I'm subtracting an x minus 2 from it, and that whole thing equals 1. And I'm a parabola, but my y is the one that's squared, so I'm a parabola that opens left or right. With this kind of thing, we said that you want to actually isolate the y bit, but the whole thing. So the y plus 1 all squared, it's fine, leave it alone. I'm actually going to move all this stuff to the other side, and I'm just adding it. So I've already got a 1, so I'll add an x, and I'll, technically this is x plus 2, so I need to subtract 2. So a plus x minus 2 ends up on the other side, and then I can combine the 1 and the blah blah blah. So, and typically we put this thing on the left hand side, so let's go x minus 1 equals y plus 1 squared. This would be the equation I was looking for right there. And if you had to sketch its graph, you would know that the vertex is positive 1, negative 1. Which is right there. And then what else would you know? I don't know. Make a little t-chart. Which way do we open? If it's y, then we're going to open to the right. So we already figured out that when x equals 1, we get negative 1, because that's our vertex. So why don't we figure out what 2 gives us? If you let x be 2, then 2 minus 1 is 1. So just remember from here, when you take the square root, am I running out of space? I very much am. When you take the square root, you'll get the positive and the negative root. So plus or minus 1 equals y plus 1. So now if I subtract 1, well, when this is a positive 1, I get 0. When it's a negative 1, I get negative 2. So what I hope is not shocking is that when x is 2, I get 2 different y values. I get 0 and I get negative 2. That should be not shocking because we're not a function. We're a sideways opening parabola. So it doesn't shock anybody to learn that when x is 2, I get 2 outputs. I get both 0 and negative 2. And those are my 2 symmetric points. And honestly, I don't need any more, but I could get more if I wanted. I could go out to 3. And if I did 3, I'd get 2. Yeah, so I don't know. I'm just going to say it. If part of the process here is taking the square root, then the next x that I should probably evaluate is 5, because 5 minus 1 would give me 4, which is nice and clean for us to take the square root of. You kind of have to think logically about this. But if you really wanted to do this way, then you should intelligently choose your x's to give nice numbers. So 5 minus 1 is 4. So now, when 4 is equal to y plus 1 squared, and I go to take the square root, I get plus or minus exactly 2 instead of some ugly radical. That equals y plus 1, which means when 2 is positive and I take 1 away, I get 1. Or when 2 is negative and I take 1 away, I get negative 3. So 5 gives 1, but 5 also gives negative 3. So 3 for 5. Positive 1 would put me here. And 5, negative 2 would put me there. So basically what we're getting is points exactly where we thought they should be for a parabola. They should be here, and they should be symmetrical over the axis of symmetry, of course. But there's my sideways opening parabola. Hopefully you understand how I got it. Concerns about my domain and range? Yes, you should have them. Because this y equation, secant t, that guy's definitely going to have a big gap. The secant of t minus 1 would have its midline down here at negative 1. It would have its max up here at 0. And it would have its min down here at negative 2. And my cosine function would start here and go bzzz. But the actual secant function would start here and go bzzz, and have an asymptote, and then go bzzz, and have an asymptote, and then go bzzz. So hopefully you can tell that my set of outputs is actually negative infinity up to negative 2, including, and union 0 to infinity. So that would seem to indicate that all this good stuff here and here, all the stuff where the y's are less than negative 2, yeah, that's fine. And all the stuff where the y's are bigger than 0, yeah, that's fine. But all this stuff has got to go. So the vertex and all that stuff that's to the left of 2, it's got to go. And again, maybe another way to see that all the stuff to the left of 2 had to go is by considering the x equation, which is tan squared plus 2. And I'm going to try this one more time to see who this sinks in for. If x equals tan squared plus 2, then think about tangent. Tangent's that guy that goes like this. And if you square things that are positive, they stay positive, they just get a little bit bigger. So essentially this half of the graph would get stretched vertically. But if you square things that are negative, they turn positive. So this whole graph would essentially reflect over the x and then also grow faster. So the tan squared t part is actually sort of forced to look kind of like a parabola. Then of course the plus 2 means that it shifts up to where down here this is now the x-axis, this is the y-axis. And this purple line is 2. Which actually shows that, yeah, if this is the equation that's defining my x's, then the x's must belong to the set that starts from 2 and goes to infinity. Meaning that's my domain. That's my domain. So no matter what my rectangular function is trying to show me, my rectangular function says, yeah, bro, it's fine. Go ahead and put your vertex at wherever I said at 1, comma -1. Well, I can't, because the x equation only generates values that are 2 or more. So this whole little bit here is gone, and I should get sort of the top half of my parabola and the bottom half, but only the part to the right of 2. And so hopefully that stuff about these implied or inherited domains from the parametric equations, hopefully that starts to make sense. My domain here would be 2 to infinity, not the 1 to infinity that you might have assumed by thinking about the rectangular equation. And my range, well, my range, you might have thought it was all reals, but when we lost this chunk, we lost a chunk. So it's not all reals, it's only the stuff from -infinity up to -2, inclusive, union, 0 to infinity. So pretty tricky. Nine. Couple more. Getting late. Real late. Okay, 9, I'm happy to say looks kind of like a cakewalk, because I'm pretty sure for number 9 I can just subtract 2 from both sides to get an expression for t. I can then take that expression and jam it into my y equation, generating a new equation where y is equal to 2 times x minus 2 all squared minus 1. And that's it. I just eliminated my parameter. This is now a totally valid rectangular equation. Very valid. All right. Now I could express this in a couple of ways. It's already in a form called vector form. And this is y equals a x minus h squared plus k. Yeah. So that form has already given us what we need. I could also kick the 1 back over to the other side and do y plus 1 equals 2 x minus 2 squared. And then this is in that conic sections form, the y minus k equals 4p. Again, I'm still not telling you what p is, but it's okay. Minus h all squared. But essentially, I mean, those two forms are so similar that I don't see how anyone could have a preference over one versus the other. You kids probably like the green one better, so that's fine. We'll do the green one. But I should certainly know right off the bat that the vertex is going to be at positive 2, -1. And because we're y equals x squared, we're going to open up or down. And because my leading coefficient is positive, we're going to open up. this was a negative 2 would open down, but it isn't. It's positive. So we know we open up. What else should you know? I'll just try to throw this out there. If I just had plain old x squared and the coefficient on x squared was 1, then don't you go over 1 up 1 and left 1 up 1, and then don't you go right 2 up 4 and left 2 up 4? I'm not the only guy that knew that about parabolas, am I? I don't know, take a hint. Imagine if there was a 2 here. Maybe I'd go over 1, and instead of going up 1, I'd go up 2. And if I go over 2 up 4, then maybe I go over 2 and up 8 instead. Anybody other than me understand that? I'm just getting lazy because it's getting late, but those are going to be the points on this particular parabola. I guarantee it. I stand by it. So why? Well, if you don't understand the trick I just did, which essentially is just using the vertical stretch here, then you know what to do, don't you? You just build yourself a t-chart, you plot some points. So when I say t-chart, it's not called a t-chart because it has t in it. It's called a t-chart because we generate x's and y's, and put a little t, say the big T. But it doesn't hurt that it also has t in it. Makes the name t-chart make a little more sense. So what just happened? I know that when t was 0, I got my vertex. Did I? Is 0 plus 2 2? Sure is. And is 0 squared 0 times 2 is 0, take away 1 is negative 1. So, yep, that vertex is definitely the point associated with a parameter value of 0. So now, why don't you just let t be 1 and negative 1? See what you get. When t is 1, I get 3. And for the y, I get 2 minus 1 is 1. So the point 3, 1. Oh, would you look at that? It's the point I already knew. And at negative 1, I get 1. And at negative 1, I get 2 minus 1 is 1. Oh, would you look at that? It's the other point that I already knew. So I don't care. I don't care how you generate your graph. Just make sure you know how to generate it one way or the other. But there's my parabola. Now, do I need to cut some chunks off of it? I don't think so. Remember, the reason why we had to cut chunks off of the parabola in number 8 was because we were defined parametrically by a secant function, and that secant function had this big chunk of missing y values. Everything between negative 2 and 0 was this dead zone of values that we don't get, which meant that my graph should have that same dead zone between negative 2 and 0. If any part of my graph tried to live there, you got to get rid of it. You got to get rid of it, right? But look here. This time, my equation is generated by this quadratic. If this was like 2x minus 1, wouldn't that just be, what, would be down by 1 and would open up? And my range would be everything greater than negative 1. And look, my range is everything greater than negative 1. So we're fine. There's no need to place any restrictions on this guy because he's inheriting the range of this y equation, which fits. It's right. There's nothing fishy going on here, so I don't need to worry about it. And finally, yeah, 10's the last one. So obviously, I'm not going to do anything from page 10. There is an answer key for that, so just look that over, and hopefully you're okay. So this last one. Again, if you've been paying attention, then you already know what it is. It's a hyperbola. And its center is these numbers, 1, negative 2. And furthermore, its center is 1, negative 2. And furthermore, these coefficients again tell me to go left, right, up, down. Is it always 2 and 3? Have they just been hammering us with that? So left and right by 2, then up and down by 3. 1, 2, 3. But again, what that really does is it just makes this rectangle. And that rectangle makes our asymptotes, which I'm going to cheat because, again, it's late and I'm getting lazy. But I would connect this dot through there. So there's one asymptote. And the other one just, we connect this vertex to the opposite vertex. So there. And then just decide which direction you open. Do we open up or down? And we know that the Pythagorean identity that we're trying to exploit here is the one where secant squared minus tan squared equals 1 in that order. So since secant is the y, then we're going to end up with a y squared minus an x squared equals 1. And when y comes first, you open in the y direction, meaning up and down. So I know my hyperbola is going to want to go like this. Yoink. Yoink. And then yoink. Okay, it's not perfect, but it's definitely good enough. And again, if you understand all that, if you can kind of pull all that information out from your parametric equations, if you can get here, then you kind of know, without doing any algebra, that your rectangular equation would be y plus 2 squared all over 9 minus x minus 1 squared all over 4 equals 1. So again, you should be able to kind of just go directly from your parametric equations to your rectangular equations without ever doing a lick of algebra. You should kind of just be able to turn the parametrics into a graph, turn the graph into a rectangular. But again, I'm going to specifically say, hey, do this conversion using algebra. And I don't know, it's easy. I've done it a bunch of times already. So what would we do? We'd subtract the 1, divide by the 2, and then would square both sides. You're not going to skip those steps, but I'm going to. You would go x minus 1. Divide by 2, square both sides, so it becomes that over 4. And hey, would you look at that? It's that. Then with the y, you would add the 2. You get, oh, actually, scribble, scribble. This would equal tan squared, is what this would still look like at this point. Then in your y equation, you'd get a y that's plus 2. It would be over 3, but I'm going to square it, so that would give me a 9. And that would equal secant squared t. Then we're subtracting. But you're not doing top minus bottom. You're doing bottom minus top. That's why we get the y first, then minus the x, and it equals 1. And that's what gives us a hyperbola that opens up and down. All right. Yeah, all right. That's it. Ugh. 48 minutes, jeepers. All right, it's like I want to say more, but I don't think there's more to say. I mean, if you've sat through all this, then you should be in good shape. So I'll just let it end. Good luck. See me in the morning if you have any questions. Bye.